Right. With today's session. Aiden, Pussy, and Matimba. Can we move
Yes, sir, we
on?
can proceed. Yes,
Yes,
sir.
sir.
Okay, cool. So, what I've just done, I'll share these questions with you. This one's from Detroit. I'll share it with you after the lesson. So, what I suggest is maybe take a picture as a solve, and then obviously, yeah, but I'll share you the collective questions we'll solve for today. All right. So I'm assuming you've all looked at the thermal pressure vessels. Before we begin, is there anything which you require understanding before I move on with this kind of problems? Anything? Nothing? Have you guys started on this already?
I
I think
tried,
it's
sir,
all
but
good, sir.
I don't understand.
Okay, Aiden, what do you say?
On my side, is it all good, sir? Does it move the thin cylinders now?
That's correct, yeah.
Yeah, so it's all good.
Oh, okay, cool. Matimba,
Hi, sir. Please, can I just be excused on voice notes? There's kind of noise where I'm at right now, but I'm listening. I'll join
no,
in 10 minutes later.
no, yeah, no worries, no worries. Okay, so um, yeah, I mean, I'm assuming you've at least watched the recordings. I'm not sure exactly what has Aiden done to prepare himself. But I suggest you all follow a similar procedure. But what's happening over here is we're looking at the stresses in a thermal pressure vessel. Um, and we can be also looking at the strains induced within these vessels as well. Um, and also for the test, you do not need to know the what's the word I'm looking for? The more stress circle. However, for the final exam, you must know that. So I have recordings for that as well. But let's quickly try and analyze what's going on over here. Okay, so there are several examples I could put of a pressure vessel. I'm not sure if you've ever seen them before. Um, I've I just want to like to just get this image for you. There are several types of pressure vessels. I mean, if obviously I'm assuming you've looked at some recordings, and then if you need some recordings on it, then I can obviously just assist you with that. But I mean, I'm here to assist you with the analysis part here. So pressure vessel might look like that over there, right? It could store gases, liquids, depending on whatever is. Typically gases, and it's pressurized, and um, and obviously as it's pressurized, we need to ensure that this structure over here, which is in the pressure vessel, is not going to fail due to that internal pressure induced by the fluid. That being said, within the pressure vessel, when it's subjected to an internal pressure, what you'll notice within the walls of the cylinder, there are two stresses present, right? If I just open this up here for you, the one you notice is the longitudinal stress, right? That's longitudinal is acting along the length of the pressure vessel. And then you get a circumferential one, which acts along the circumference, right? So there are two stresses induced. There is a third one through the walls, but for the third ones, these are important. Are we all on the same page with this at least? Understanding there are two stresses present in the thin wall pressure vessel. Please talk, guys. We're on the same page here.
Yes, sir.
Okay. And the formulations for those individual stresses, obviously it's developed from first principles. It's shown some in your book. The stresses are as follows. It will be P, the internal pressure within the vessel, the diameter, the mean diameter actually, but we just call it the diameter, 4 times the thickness, and then also times the efficiency over here. Okay, there's some kind of efficiency. So now what I wanted to look at is the following. Let me just quickly share with you, because I've noticed that the formulas are not, and I mean, this is highly recommendable for the test. And we're going to solve an exam paper question like this after this particular question. So please pay attention. So what I'm going to do now, I'm just going to the end of the chapter and just want to screenshot those formulas for you so you can see it over there. Okay, yeah. So I'm going to ask a quick question to the house, colleagues. If you look at the formulas, right, you notice that in the longitudinal stress, we have an efficiency of the circumferential one, and we also have an efficiency of on the circumferential one, we have something on the longitudinal. Can you guys see that there? So can you see that the subscripts are different? Can you guys see that there?
Yes, sir, we can.
Okay, so why do you think we are using why are we using the circumferential efficiency, right, which is essentially of the joint on the longitudinal side, and why are we using it on the why are we using longitudinal on the circumferential side? What are your thoughts? Aiden, seeing that you've went through this before.
So I think that you do is opposites because by the circumferential stress, it is going to be the longitudinal efficiency that is going to resist it.
That is correct.
So yeah.
Yeah. So as you said, like, so if you look at the longitudinal joint, right, the longitudinal stress wants to break the vessel like this, right? It wants to, oh, sorry about that. Why is it, okay, there we go. It wants to split the vessel in that direction. And the joint keeping it together is a circumferential joint, right? Whereas the circumferential stress wants to split it the other way, right? Or that way, as you can see over here. And the joint, or rather, you know what I mean, that way. And the joint keeping that two plates together is essentially is the longitudinal joint. So that's a very important concept which is mentioned. So when you're dealing with the stresses, be cognizant of the fact that when the longitudinal stress is coupled with the circumferential joint efficiency, and your circumferential stress is coupled with the longitudinal joint efficiency. I hope that's clear to everyone. So let me try and do this one. Please ask questions as I move along. So I'm going to give you one similar to do with this. And then, yeah, and then we're going to move on to maybe I have another third note question. Maybe we can do some, what's the word I'm looking for? I'm realizing now that's not the question I actually wanted to do. I'm going to just screenshot it now. It's from the Du Toit textbook. It's this one over here. I got it now. So just bear with me. It's this one over here. Yeah, sorry about that. This is the one I actually wanted to do. Okay, perfect. Cool. So let's try to embark on this question. So here they're stating the efficiency of a longitudinal circumferential joint of a shell plates of a boiler, that's one of the cases of a pressure vessel, or 2.7 in diameter, and the efficiencies are 72% and 45%. So let's put that there. I'll write this down. So our diameter, or D, like a small d, is equal to 2.7 meters. Our efficiencies of the longitudinal joints are 72%, And then our what's it, circumferential is equal to 45%. So this is not typically a good joint. Obviously, it should have a decent efficiency. This is probably a poor welder, right? Unqualified welder welding here. Nevertheless, they're saying the boiler's pressure is 800 kilopascals, right? And what they want us to determine is the shell thickness. If the tensile strength of the plate is 320, assume a factor of safety of 4. So if you look at the equation over here, right, we are looking for T, right? Can you see that there? It's just a manipulation. And we have all the individual other parameters. But before we begin with the question, we need to look at what is this about? I don't know if I mentioned to you what the factor of safety was. It's your maximum, right? Given here, right? Your tensile strength divided by the allowable one. So what we're working with is this here. Okay, so we need to first solve for the allowable stress. This is mentioned in the first chapter. I'm not sure if you've had a look at that. But nevertheless, so we need to find our allowable stress, which is quite easy. And that's going to be simply 320 and then divided by the 4, which is given. So I'm just manipulating this question over here. If you do this, you should get 180 megapascals. Okay. Is that fine to everyone? Is everyone familiar with the concept of factor of safety before we move on? Please say no or yes if you don't know, so we can make it beneficial. Nothing wrong if you don't know.
No, sir, I don't.
You don't. So you haven't looked over that. Anyone else? Okay. Aiden, are you familiar with it?
I've seen it before, sir. But
Okay.
we can go over it again.
Yeah, I'm just gonna quickly mention to you. It's not a crazy concept. I'm just gonna pull out a piece from the book here. Yeah. So we can have a look at it. Let me just share the book and then we can just, of course, both books should have this particular thing. Let me see over there. Oops, sorry about that. Okay. So this is the factor of safety over here, right? So what they state here, I'll reading to you. They're saying when design engineers are designing a machine with many components, they always include a factor of safety in the calculations. For instance, just to give you a state example, a lift cable might indicate a maximum load of 1,000 and the factor of safety is 2. That means a cable break at 2,000 kilograms. So whatever we build, right, as engineers, we never, like you normally see maximum capacity on the lift or anything. We will normally say maximum load of 1,000, even though we know it can take 2,000, because you know what's going to happen if people obviously purposely overload the system. Another example here is just reading off the book. He says, what do you think what would happen if an aeronautical engineer designed aircraft need to be strong enough only for good weather and perfect flying conditions? Everything might be fine on a clear sunny day, but what happens if it travels in storms ahead? So obviously we've got to think about that. So we need to kind of design it for the more stricter or more stronger material, in this case over here. So you can look at a few of these types of examples over here they give you, but long story short of what the factor of safety is basically equal to, or you can have like this, your allowable working stress, which you just worked out now, is the ultimate stress, right, divided by the factor of safety. Also, in terms of the yield limit, it'll be the working stress equals the yield over your factor of safety. What I like here, what they say is that the factor of safety depends on a few things: type of material, the job, which the component is meant for. And then here are some typical factors of safety depending on the application. So if you're dealing with a steady force swimming using a ductile material, we might have a factor of safety of 4. You guys with me? Maybe if it's a brittle material, depending on which criterion we use, we might have a factor of safety of 6. If it's a shock force, you obviously want a bigger, a bigger type of factor of safety, maybe 10. And obviously, if you're looking at the brittle side, because the brittle material, because it's not ductile, we want to, choose a 20. So you guys get the idea of what a factor of safety is? Is there any uncertainty with this?
Thank you, sir. Now I understand.
Yeah, so basically, how do I say, man? It's just a safeguard we put in the event that the thing gets overused. Another example might be, this is another type of example of a factor of safety, but not exactly. Like, your petrol tank on a car. I'm assuming we've all driven a car before. And when the gauge comes on, the empty gauge, when you don't throw petrol in, it's basically telling you the car is empty, but we both know that the car is not really empty. We can still push the car a bit. So it's that kind of, so obviously with the petrol tank itself, it has some kind of factor of safety. You know what I mean? We don't know how many liters or whatever. In that case, or factor of safety. But we apply the same principle to structures as well. So even though the structure can handle 3,000 tons, we say, oh no, guys, we can only handle 2,000 tons or 1,500 tons. Because people are always going to want to be extra. Okay. Is that fine for everyone?
Yes, sir.
Yes, sir.
Perfect.
Thank you.
Okay, let's move on. So it's nothing crazy. It's a simple equation. Just it's used in design all over. Okay. So in that case, we know our plate can handle 320 megapascals, but we say, oh no, we are, depending on the application, it's a boiler, only 180 megapascals. So now I'm going to do the first part and I want you to do the next part now. So then we're going to work on this formula. So what we have to do now is determine a suitable shell thickness. So we have to do it for both stresses, right? Both circumferential, both longitudinal. Don't have to do it for both, but anyway, it's just the way it's presented. We can do it like that. So it's 40. Okay, so we just populate. The stress, in this case, the stress is given 180 megapascals, right? It's going to be for both. So a lot of things I can mention with this, but anyway, so 180 there, our pressure was given as 800 kilopascals. And our diameter was given as 2.7, okay? And then we're going to say 4 times the thickness, or we do not know the thickness. And then you times it by we're doing the longitudinal, you must times it with the circumferential joint efficiency of 0.45. It's a percent, right? We algebraically manipulate this, and this should be 800 times 10 to the power 3 times 2.7. What is it? And then we're dividing by 180 times 10 to the power 6 times 0.45 times 4. The people at John Thompson and they're boiling boilers, before they roll up the plate, they definitely do a calculation similar to this. Can we just get the thickness, please, colleagues? So remember, I'm just going to give you some context before you just quickly calculate. So how do you want to work the thickness? So when a bowl, pressure vessel or boiler, are you guys familiar with the rolling process? Does anyone know what the rolling process? I'm using a very plate rolling, so manufacturing. So can you see over here? We're boiling one of the shells on the vessel. Can you guys see it? So we take a flat plate and we basically, you know what I mean? We roll it into a cylindrical thing. Can you guys see that?
Yes, sir.
So what I'm saying is, how thick must this plate be depending on our conditions given? You know what I'm saying to you? So that's that thickness of this plate we are working at. Okay. Let's get that thickness quickly. Please don't take too long so we can move nicely.
I got 0.006.
Can't be, man. Can't be 0.06. No worries. Check again. Unless my math is wrong here. What's 180? What's 180 times? No, man. I think I see my mistake. What's 320 divided by 4? It's 80. Okay. Yeah. Sorry, right. Pussy. It's 80. It should be 80. The math is wrong here. It's not times 2. Here we go. Hope you guys are with me. It's 80 MPa. Yeah. And just redo the calculation. There you go. It's 80 megapascal, not 180. What do we get for that one?
I got 0.015.
Yeah, that's correct. How much? What is that in meters? Or I mean, in
Meters.
millimeters?
Meters.
Yeah, that's going to be 50 millimeters, right? You agree with me? Colleagues, do we all get that?
Yes,
Yes,
sir.
15 millimeter.
Oh, yeah, perfect. So then what I want you to do now is use this formula, right? Which is the circumferential one, which is over there. Okay. So it's going to be PD 2D, and the joint efficiency is now the longitudinal one, right? I'll just bring down the question for you a bit so you can see. So I want to do the same thing here and solve for T for me, right? So I don't need to do that part. You guys can do it. So give me your thickness over here. What is your thickness? Same calculation, just obviously there's slight parameters which is different here. What thickness do you get
I
there?
got 30 millimeters.
Sorry, how much?
I got 30 millimeters.
No, it can't be 30, man. Check your joint efficiency, pussy.
Okay.
It's not 30 for sure. I have the answers in front of me. I've worked it out. Maybe I should write this here as well. So plate stress is this. Pressure is 800 kilopascals. Okay, again, if you want to see this work, go to any place with balls, any kind of pressure vessels. In this case, John Thompson is one of them. And our efficiencies are 0.72. But remember that your deficiencies are interchanged. Not interchanged really, but you know what it is, as long as you understand what's going on. So let me know. Check out.
I got 18,75
That's correct. Yeah, millimeters, right?
millimeters. Yes.
Okay, perfect. Colleagues, are we all happy with this?
Yes.
Aiden, Matimas, and Piwe. Thank you, brother. Okay. So here we've got our 2 plate thicknesses, but it says we must determine a suitable shell thickness. So we only have to choose 1 plate. Which of these plates are you going to choose? And why? So we've done the analysis, but now we need to make a decision making, right? So which plate do we choose? Now I need to think about it. Do we choose the 18 mil plate or do we choose the 50 mil plate?
We should choose the 18 millimeter because the thickness is a little bit thicker than another one.
That's very good, Mr. Faku. That answer is correct. It's thicker, but not only because it's thicker, there's any other reason why. But you're definitely right. Can we check something? Can we do a calculation to prove that you're right? Colleagues? Aiden, Busi, do you have any points before we maybe perhaps do a calculation to prove that Mr. Faku is right?
We can do the calculations, sir.
Okay, perfect. So remember, we're limited to only 80 megapascals, right? That is for our current design. So if we, let's say some intern decides, okay, not intern, sometimes the CEO or the manager on top of you doesn't have a qualification. No, we can't afford a 20 mil plate in this case, right? You must buy the 15. Let's use it for this. So let's quickly take this plate and put it into this calculation. So we have 800 kilopascals. We times it by 2.7. Okay, we divide this guy. 2 times 15 mil, right? Is that fine? 0.00015 times 0.72. Can you just give me what stress we will get here?
So that's gonna be 100 megapascals.
Can colleagues, you agree with that? Give another comment as well.
Yes, sir, I agree.
So, will that plate be suitable? Yes or no? We'll see. Are you thinking? Who's that? Will that plate be suitable? It will not be. Why? It exceeded. You see here? It exceeded the 80 megapascals. You understand? Are you with me? So there'll be more stress because you're using a thinner plate, which is not desirable. Because you're only limited to 80 megapascals. Is that fine for everyone?
Yes, sir.
Yeah, and remember
Yes.
that does not apply. Yeah, this doesn't apply to when you're selecting diameters. Diameters is a bit different. I'm assuming you've watched the recording, which explains that. So I'm just making you aware of this particular case. So would you guys like to try to solve a problem on your own, like this? Is it fine?
Yes, sir.
Okay, cool. So this one, and you can make a note of it as you write it. I'm gonna put it up. It is from the 2024 April paper, past paper, the 19th April 2024. So last year. I'm gonna put up the question here, and you just have to do for me 7.1 for 7 marks, just there. It's a very popular question. Might not come in the test, but it's worthwhile doing. We're not going to do number 7.2 yet, but let's quickly determine the minimum thickness. So I want you guys to do this for me. I'll just tell you if you're right or wrong. That's fine? So the same principles apply. The only difference here is that we have two different plate material, one for the circumferential stress 600, one for the longitudinal 560, and we have a factor of safety of 5. So we'll make sure we divide this one by 5 and that one by 5 as well. Hope that's clear to everyone. So when you're done, you can just shout out the answer, and I'll confirm. I'll write the right answer there. So your circumferential stress, allowable stress should be circum 120 megapascals. And then your, what's this, longitudinal? Allowable stress should be 560 divided by 5, which gives you 112 megapascals. Let's see the thickness of plate. And remember, whatever plate you select, right, you should state there. Use plate thickness of so much, it should be able to withstand both pressures, both strong enough for both joints. They normally give a mark for that. Stop publishing in module 7's. Right, colleagues? I don't want to spend too much time. We have 2 minutes left. We'll see Aiden, Impure, what thickness did you get? Should be a quick calculation, I think. You guys still working on it?
We're still calculating, sir.
Yes, sir.
Still working on it, eh? Okay, come on, guys, man. Let's move.
Sorry, sir. Can I ask a
Yes.
question? So
Yeah.
do you calculate both thicknesses and then you determine which one is the minimum thickness or what?
Yes, that's correct. Yeah. The minimum
Okay,
being the, yeah, sure.
the minimum thickness I got here is 4,209 millimeters.
Let me just check quickly. So remember, it cannot be 4. No ways. That's too thin. 4 mil is too thin.
Oh, I saw my mistakes. Okay.
Yeah. So they're saying the word minimum, but I don't want you to choose the thinnest plate, you know? As we've established, we have to choose the thicker plate of the two, which comes out fairly obvious.
So my thickness is 0.037 meters.
What's it? 0,
Zero.
0, yeah.
0.037.
0.037. Is that your answer?
Yeah, so that's gonna be, well, I think it's gonna be the suitable minimum thickness.
Can I ask you, what is your other one? So this would have been on your circumferential one, right?
On my circumferential one, yes, sir.
And this one over here?
That's gonna be 0.021.
0.021.
21, yes, sir.
Yeah. And Ian is correct. This will be your minimum thick plate. It'll be 37 millimeters. And you must state there, use plate thickness of, yeah, that's correct, yes. You're going to get this. Of 37 millimeters. It will be able to withstand both joints, or strong enough for both joints, yeah. So on and so on. But you must state the last statement there. They give you a mark for that there. Colleagues, if you all get this, time is going here. Tafaku and Busi, do you guys get that? Okay. Busi and Simbiwe, do you guys get that?
Not yet, sir, but we can continue.
Oh, okay, that's fine. Mr. Falco,
Yeah, not yet. No, not
you
yet.
guys
I
are-
don't know, because I was just getting 39.2. I'm not sure.
okay. Yeah, okay. I guess you can just have a look at that.
Okay.
So, yeah, should I continue with module 4, or should I move on to maybe a question in module 7? What do you guys like? Because module 7, I do have recordings available, obviously.
So you say now for module 7, you do have a recording.
Yeah, I've got a few there.
Yeah, but I think maybe it can work also, the recording.
Okay, are you guys?
Then maybe
Yes.
we can continue with this one.
Okay, are you guys watching the recordings? Are you gaining anything from it? I'm just checking.
Yes, sir, it's very helpful.
Okay.
Because we can also get that to check what was wrong with it playing back and bringing forward. So they help a lot. So
Okay,
currently
great.
now.
Yeah, now I'm just checking. And if you want me to solve any particular problem, you must put in the group, guys. You know, I'm there to assist you. But I guess it's quite okay. Let's continue with module 4. So I chose another question from the toy textbook as well. And it's a bit of a different one. And yeah, so again, the all assist up and coming, what is this, test, and of course in the final. So yeah, just remind me, when are you guys going to be assessed again or for test 2? What is the date?
We're writing on the 6th.
Okay, so that's next week already.
Thursday.
Huh? Oh.
Thursday, yes.
All right, so let's try this one. Yeah, we have a thin cylinder or cylindric cylinder. Don't know why they're mentioning that. Probably a mistake. There's an inside diameter of 1,000. That's a meter long, 5 meters in length. It's made from 10 mil thick plate and is subjected to an internal pressure of 3 megapascals. The Young's modulus is 200, and we have something called the Poisson's ratio 0.3. Okay, so what this is about, let me just quickly put up an image for you. So now we're looking at the concept of strains within the vessel. And I'm just going to find the image which I had earlier on, which I'm just trying. Okay, yeah, these. So let me just demonstrate that like this. So if you have a circle, assume this is a perfect circle, or if it will adjust itself. There'll be internal pressure acting due to the fluid. And obviously, as the fluid exerts pressure on the holes, we'll obviously see there'll be an increase in the diameter, right? There'll be some increase. I hope everybody can understand it. There'll be a change in diameter there. Is that fine, right? That makes sense, right? We've talked about this in the other chapters in a different way, right? So we have internal pressure, and the vessel itself will increase by a certain amount. That's that change in diameter. Likewise, if I draw a vessel on a side view like this, obviously we have internal pressure all over here in the walls, and it'll be like that. And what we find is that the vessel will also obviously increase in length. You know what I mean? The pressure will make that a bit longer. So that's what I mean by this space here is called the change in length. And obviously, when we're dealing with lengths or diameters, we can obviously then understand that there's a change in volume of the whole thing. I've seen this happen where we do hydrostatic testing before we commission the vessel. And I just can't recall to what pressures according to the standard. So you normally want to test it like, I can't basically call, maybe let's say 1.5 times the design pressure. And you actually notice, especially with doing with thin stainless steel plate, it actually will bulge up and it will actually increase in size. So what we're just looking at is now the strains, or rather the change in length and strains due to this pressure. I hope that's clear to everyone. So now I'll quickly just remove this and then just go to the book just to show you a few things. What's nice of this part is just like the previous part, as long as you understand the formulas, you should be fine, right? Normally I don't teach formula-based work, but I guess for this over here, it's what's required. Okay, so I'm just going to quickly show you the text for this, and then just go over it briefly, then show you. So as long as you understand what the change in diameter is, and then what also is the change in, yeah. So looking at these formulations, it starts over here, right? Strain. There is something called Poisson's ratio, which talks about the longitudinal and the lateral strain. I can show you a video of that, but what it basically is, it's as this thing in, so let's say we have this original thing and we pull it, we notice that the area gets smaller and the length gets longer. the ratio between that two change in length or expansion is called the Poisson's ratio, right? It's a separate thing on its own. But in our case, we're applying it to the following. So the longitudinal strain in the cylinder, right, is basically equal to this formula over here, right? And again, they're not properly deriving these formulas for you. So you're just gonna have to take it as truth. And obviously we know that strain is also equal to change length of a length. So you can also put this in terms of change of length. We take that EL, longitudinal strain, which is essentially all of this. We put it in there and we get this formulation over here, right? So this formula, I believe, is given in your formula sheet. So if you want to calculate the change in length, you're going to want to use this formula. Again, that V, side V, italic V, is called the Poisson's ratio, and all other parameters, as you know. So that will tell you how long the vessel will extend under that particular pressure. Similarly, we can also look at the change circumference or the diameter. And the circumferential strain is equal to the change in D over D, just like change in length over length. And then they develop a nice formulation for you, which is just basically PD squared over 40E, 2 minus the Poisson's ratio. That's all you have to know now to apply it. And then the last one is to look at your volumetric strain, which you'll notice it's EL plus 2 times ED. Reason being, you have two cylinders on either end, and this is the length in the middle. And your volume formula is basically change in volume, PD over 40E, bracket 5 minus 4, Poisson's ratio times the volume. So if you have those formulas, right, you should be able to calculate all of this. I hope that's clear to everyone, huh? In terms of how that works. And I have presented a video on this particular part. So if you want to go over it, I'll send you that recording you can go over. And again, more stress circle won't be in this upcoming test, but make sure you're prepared for your final. So let's quickly see. So I'm just gonna put up that formulas for you, and then we're just gonna apply it straight away. So all the questions I'm taking is coming from the summative assessment, by the way. So I'm just gonna take these formulas here. Yeah. And we're just gonna use them. Okay, that's simple enough, eh? So I want to try the first one, and then I want you to try the other one, just using the formulas given here. Okay, so let's do 5.1. So we're looking at the change in diameter, and all we have to use is that formula over there, right? We want to see how the diameter has increased, right? We're not expecting big numbers here, by the way. Otherwise, it obviously would mean the structure has failed. Simple formula. So the pressure is given to you as 3 megapascals times by the diameter of 1. We square, divide that. 4. Our thickness is given as 10, right? So that's 0.01 times E, which is your modulus, as you know, 200 gigapascals. So this must be steel. And we're just going to say 2 minus the Poisson's ratio of 0.3. By the way, this also changes depending on the material, but typically you're working with these values. All right, so what did we get for this one? Can you guys quickly calculate that for me? Let's get used to the calculation. Straightforward, eh? There's no other tricks here. I know why is it for 10 marks? I think I know why. Because they're calculating in a different way, but that's all they want. That's a change in diameter. Make no sense why there will be 10 marks. It's beyond me. Yeah. Tafaku, Matimba, Aiden, Pussy, you guys there? Just quickly calculate that one for me.
Sorry, what are we calculating, sir? I
change
only
in-
see the formulas here.
The change in diameter. That's over here. 5.1. And what you want to do next is calculating the change in length, which is this one here. I hope that's clear to everyone.
Sorry, sir.
Yes.
The all I'm seeing here is the formula sheet. Can you maybe go back to the question? Because I don't have the values.
Oh, I did. You guys didn't say anything, man. I didn't share. I was busy writing, but then I was the whiteboard. Here's a whiteboard. I was sharing the book now, right?
Yeah, sir.
Yeah, there we go. You see it now. Sorry, man. You didn't say. Yeah. Can you guys see what I'm talking about now?
Yes, sir.
Forgive me, forgive me. There's one thing now. What's going on? It's fairly straightforward. Fairly. Yeah. Sorry about that. Colleagues, are we winning?
So I got 0.638.
Yep, that's
Times.
correct.
Yeah.
Yep. Straightforward, right? So that's around what? That's 600. No, are you sure it's
Times 10 to the power of
millimeters?
-3. So
Yeah, that's what I was gonna say now. Yeah, it can't be that big. Yeah, so that's 0.6 millimeters, eh? Okay. So if you're done with that one, you can do 5.2. And 5.2 is simple. You're just using that formula over here. There is two approaches to calculate 5.2. And maybe we can look at both. Let's quickly see let's see if this is gonna work out. The change in length equals PD over 4TE. And then we have 1 minus 2 times Poisson's ratio. Okay, just get that for me. Just a plug and play. We've already omitted a lot of the strain stuff, which is all strain analysis, but yeah, it is what it is here.
I got 0.15 times 10 to the power of -3.
So it's 0, comma?
15.
Oh, wait. You must times about the length, eh? Times about the length. See here? Times L. I'm realizing that now.
Oh,
Yeah. What do you get for that? So the length is, sorry about that, that's going to be 5. Times right, 5, eh? Which is the length.
So it's gonna be 0.75
Perfect.
times 10 to the
That's
power.
correct. Yep. Times 10 to the power negative 3 meters. That's it. That's it. That's how simple this is. The other way of doing it is calculating your longitudinal strain, right? Which is going to be 1 over E times your longitudinal stress minus your Poisson's ratio times your circumferential stress. Once you have your longitudinal strain, that's basically equal to your change in length divided by your length. So what you notice that this part, the strain EL is basically this section over here. You see this over here? This piece over here? See that there? That is actually a longitudinal strain. If you're actually looking at the formula properly. Can you guys see that?
Yes,
Yes.
sir.
Yeah. So I'm making you aware that you can just use the formula, but what I'm showing you is that this part here, the PD, all of the stuff here is basically this section over here. That strain over here. So they ask for the longitudinal strain. You can calculate it using this formula over here, which is essentially this formula over here. This and that's the same thing over here. Just being clear to you. Okay, let's try the last one. And we look at 5.3, which is quite simple, and they're asking us to calculate the change in volume. Again, it's a plug and play game. Nothing fancy. Right? And that's going to be P D over 4 T E 5 minus 4 times Poisson. And times the volume. Okay, so just do that for me quickly. Very important concept. I don't need to put the values in there. You can quickly find, and it'll give you a change in volume. How the volume change for that pressure.
What's the volume, sir?
So we have to compute the volume, right? Is that correct? What is my volume formula equal to? What's volume of a cylinder? You know?
It's gonna be pi dt.
ET, no. Pi over 4 D squared times L, right? That's the area. Am I right? Times the length. Got that?
Yeah, sir.
Yeah, so that's it. So now you must calculate, you have the diameter and you have the length. The length is given as 5. So I calculate the volume for you here, it's pi over 4. That's going to be, diameter is going to be, what is it? 1, eh? 1 squared times 5. And that should give you an answer of around 3,927 meters cubed. Guys, please know your basic mensuration formulas, the volumes. So what do you guys get?
So I got 5,596 times 10 to the power of negative 30.
Let me just confirm that. So again,
5,596.
that's correct, yeah. Times 10 to the power negative 3 meters cubed. That's it, colleagues. Nothing more, nothing less. That's it. Is everyone happy with these formulations? Busi, Simpiwe, Matimba? Will you guys do that?
Yes.
You sure?
Yes, I'm good, sir.
Okay, so now let's end off now. And I want you to find the volumetric strain. So the volumetric strain, if you hear the word strain, is for 7.2. The volumetric strain is quite simple. It's going to be a change in V over V. Is that clear to everyone? Your longitudinal strain is a change in L over L. Your circumferential strain is changing D over D. So obviously your volume is that. So what we first must do here is we need to calculate our volume, and then we can calculate our change in volume using the same formula. So my volume for this one, I'll do it for you here, pi over 4 T squared L. Our diameter is 3 and it's 4. So it's pi over 4 times 3 meters long. That's 3 squared, and we're timesing this by 4. Let me calculate the volume for you. And all you got to do is calculate your change in volume. And you should get 28.274 meters cubed. Is that fine for everyone? Quite straightforward, eh? There is another alternative to calculate your change in your volumetric strain as well. Can you calculate your change in V for me for this one? We're all on the same page. Colleagues, are you all on the same page?
Yes, sir.
Perfect. So I'm sending you two videos, which is from one of my favorite channels explaining Stentor materials with animations. So I encourage you guys to watch that as well. And then I'll send the individual videos. Aiden, you tell me when you want. You ready for Module 7's videos, no? I don't think I sent that yet.
Okay, sir.
And Aiden's the only one who's actually saying stuff in this group here. I don't know why. Engaging and so on. There was people eventually, then yeah. I think Aiden, I don't know why Puss is so quiet as well. So let's quickly get that down. Matimba, what is your surname?
Nkuna.
Puna. Okay, I see you here. Okay, So what do we get for the change in volume? Volume, and yeah, we need to change in volume in the volumetric strain. And you'll notice in the past paper, it'll give you from the April, it'll give you another approach, which is great. So you have two approaches.
So I'm stuck. I don't. We use this formula that we just used, not the PD over 4.
Yes.
DE. No.
Yeah.
But
4 TE, right? No?
yeah, so
And then
but
your
I don't have Young's modulus.
Okay. So it's 5 minus, okay. So what I recommend here, that's at 5 4V. Yeah, I remember that, okay. So what I recommend here, if they're doing this now, they probably wanted to use the other approach. But before we do that, let's quickly just assume a few parameters, right? So we're going to assume E to be 200 gigapascals. And let's assume a Poisson ratio to be 0.3. Okay, just quickly do that. It's going to work out first, man. So that it possibly means that we need to use another approach. You know what I mean? They want us to use the other one. So we're assuming. Assume E and that. So the pressure was given as 2.2. You'll check that approach now. Don't worry. Thickness was given as a thickness must be the thickness we've got here, which is 0.07 or 37, sorry, times 200 power 9 and 5 minus 4 times 0.3. I'm just interested to see what answers we're going to get. So then I have to show you the other approach. I'll show you the other approach. Don't worry. I'll just show you so long here the formula, what it looks like, the other approach looks like. The other approach, while you're working, you'll notice that the volumetric strain is equal to your longitudinal strain plus 2 times your diameter, your circumferential strain. So that's the other approach on how to calculate it. But let's see if our assumed values will work out here. Who's the item you guys manage?
So I got 0.024.
0.024. Okay, that's meters in the power. Clean meters cubed, right? So therefore, our volumetric strain must be a change in volume over V, right? Let's quickly see it's going to come out. I have the memo in front of me, yeah? And then we just say divide by 28. I want to see if we're going to get the same answer. But remember, we're just assuming here, so it's not actually correct. It's actually correct, but not correct. Just want to see what we get for that.
That's 8.488 times 10 to the power of -4.
Okay, so that means we can't do it this way. 8.4. Second 4?
488.
488 times 10 to the power -4, right?
Yes, sir.
Okay, so that's going to be, there's no unit for this. So this here is if we assume those values. If we use assumed values. So this is not, I wouldn't say it's not wrong, but Yeah, obviously the question doesn't give us that, as Aiden said. So now we've got to look at another approach. So it's quite simple. So if they don't give you these values, the E and the Poisson's ratio, we're going to have to work on these ones over here, right? So your volumetric strain is your longitudinal strain, that's in the center, and then we have two, remember, two circles on the cylinder. So then we have to use that, the formula for this one and the formula for that one, right? Which I'll show you now. If you remember, I did show it to you. So the formula for your longitudinal strain will look like this, right? It's not a bad exercise we did, so we can actually see. So this is the one formula. Okay, well, so that's the one. Let's delete that one. So that's that over there. And then for our diameter, so let me see what's here. Circumferential strain will also have its own equation there. Just want to find it for you. I'll just paste it there for you. Yeah, doesn't have an equation for circumferential strain, it seems. So that, no, they must have one. Doesn't make sense. Don't see it here though. It should be here though. We'll just check the Wickens textbook now, if it's there. I don't see it here in the yeah. So this one, you want to calculate your longitudinal strain. Otherwise, you must go the whole way around, basically. Let's quickly go back. So that means, but then again, there's also 1 over E. So what I can tell you here right now, that they didn't specify. I'm looking at this equation here, and we should have gotten the right answer, because you need E and you need Poisson's ratio. So I'm not sure why we got two different answers. And I'm assuming, Aiden, you sure these values are correct here? Is everything correct here? I'm going to show you now. I'm just screenshotting it quickly. Yeah, no, but we should be right, man. There shouldn't be a problem. I'm just realizing now. Okay, so that's fine. I think we can call it here. I'll put up the answers to 7.2 now. You'll see it in the group. But what we did was perfectly correct by assuming those values. I'm just checking if we didn't make a mistake with these ones here. I'm just going to confirm. So my volume is definitely right. Oh, Aiden, you forgot something. I forgot something. Times by V. Times by V over here.
Yes, I did.
Okay, you did. Okay, cool. So let me just do my thing again. That's 2.2. No, so we did the right thing, man. Of course. And our thickness was 37 more. You should see the answer in the group there. 200. So I always know the rule of thumb is you always have to assume values. Even when you write your GCC, assuming is perfectly normal. Just by the way. So it's 5.
What do you assume wrong then?
No, it's not. You must know what you're assuming. So Aiden, no, I mean, it's really, you have to know what you're assuming. Like if you must assuming certain material specs, man, like aluminium is around 70. It's correct. But my change in volume is a lot different from yours. Mine is 0.007985.
I think it's because you forgot the diameter, sir.
Oh, I see on top. Perfect. Okay, so diameter is what for this one? 3, right?
3.
Yeah. Okay, cool. Yeah, no, you're definitely right. Yeah, no, for sure. That's correct. Answer. Let's go here. 0.0. So you are definitely allowed to assume certain stuff like standard values and so on. 28.274. Yeah, no, that answer looks correct, man. So I'm not sure what's happening in the book though. But anyway, so have a look at what I did in the paper. Let me know if there's any sticking points with it. I'm pretty confident of our answer. I'm just looking here. What would be the possible cause? I'm comparing our, okay, let's see volumetric strains. I can't really compare. You should have gotten the same answers regardless. I'm just looking at it. They don't use the plate thickness here, so it's fine. Okay, cool. So let me just quickly see what they did. I see what they did. I see what they did. I see what they did, which is not entirely correct. Yeah, I don't think the memo is correct, but anyway. Okay, guys, thanks for a fruitful session. I posted some two stuff. Aiden, you are seeing that you're the champion of the group. You let me know when you're ready for module 7, and I can post the recordings for that. And again, guys, if there's any particular problems you want me to work through, tell me so I can work through them. You know, whatever support you need. So I'm not understanding this, put in the group, I'll respond to you and you'll be fine. Scope is the same as follows. Focus from 2021 to 2024's papers, you should be fine. In fact, to 2023, yeah. And make sure you go over the parallel arrangement again. It should be parallel arrangement with, you know, the one of the resultant stress, that kind of thing. And yeah, but if there's any questions, please come in the group, put in your work. Sir, I can't do this, and I will assist you. Okay, guys, thank you very much. Cheers.
Thank you, sir.
Okay.